Hello, everyone. My name is Mariusz ZAL. I'm from Poznań University of Technology. Today, I have pleasure to present my paper, An Efficient Power Control Plane for Switching Nodes. My presentation is prepared as follows. After short introduction, I will present closed switching network architecture. Next, a few words, maybe even more than a few words about control plane power consumption, measurements methods, simulation results. Of course, my presentation finish conclusions. In many publications regarding the reduction of electrical energy consumption in IT sector, various methods of reduction can be found. However, perhaps the most well-known classification is the one present on the slide. This group of method is divided into three groups. The first group is a re-engineering. Is the re-engineering of devices or entire systems. Here we distinguish the method associated with efficient silicon as efficient integrated circuits. Another way in this group, the first group, is to reduce the complexity of electronic circuits. Less complex circuits, of course, consumes less energy. The second group, the dynamic adaptation, adapts to load condition prevailing in the network. The third method is device of element slipping. Of course, this group is also divided in many subgroups, not presented on the slide. One of the frequently used solution in this group is called dark silicon, which involves tuning of entire device of parts in order to avoid static power loss. In my work, I considered switching nodes. A switching node, as shown on the slide, is constructed with switching fabric presented in this part. Input and outputs elements to which the input and output of switching nodes are connected. Additionally, each switching node contains a control module and management module. The power supply module is also an essential component of the switching node, although it is not shown here. Switching nodes are abstract devices, but there are many implementations of such elements. For instance, switches in internet networks, routers in IP networks, or telephone exchanges are all examples of switching nodes. The switching fabric is the central element of the switching node. Here are various architecture of switching fabrics. In this research presented in this paper, I focus on the closed switching fabric architecture. Such switching architecture is presented on this slide. The closed switching fabric is built with three sections of switches. The first section, second or middle section, and the last or the third section of switches or switching element presented here. The first and last section is constructed with R switches of size N by M or M by N. The middle section is built with M switches with size R by R. The entire switching fabric has N inputs and N outputs. To reduce electrical energy consumption in switching nodes and consequently in closed fabric, existing solutions already implemented in devices can be utilized. I'm referring to the mechanisms implemented in the control plane that allow monitoring the current traffic intensity offered at the inputs of switching nodes. So this information is collected in the inputs and of course sent to the management or control plane. In many devices such as routers or switches, we can find information about received and transmitted packets, bytes, and similar statistics. In the case of seeking to reduce electrical energy consumption in the data plane, it is possible to disable certain resources, such as switching element in the switching fabric. For instance, in the middle stage of cross-switching fabric, it is possible to turn off one or more switching elements, depending on, of course, of the intensity of traffic offered and the input of network. When we turn off one or more switching elements in the middle section, we save electrical energy. In the closed fabric, it of course is not possible to disable only inputs or outputs element. Of course, if we know that there are no users that are connected to the inputs and outputs to particular input and output switches, we can disable, we can turn off such switch, but it's not recommended. All implementation based on the middle section. How is electrical energy lost in an electronic system? There are two paths through which this energy is lost. The first is leakage current, which is the flow of electronic energy to the substrate. Reducing the losses caused by a leakage current is possible by developing new, more energy efficient electronic circuits. So the first group of methods for electrical energy consumption, re-engineering. The second place where electrical energy is lost in semiconductors circuits is switching current in transistors. The faster the transistor switching occurs, the greater the energy loss in this manner. This is due to transistor imperfections and interjoint capacitances. Measuring electrical energy consumption by the control plane is an extremely challenging task. The control plane is one component of the entire devices, and it is difficult to isolate only the control plane at the power level. Besides the challenge of isolating the control plane electrical energy consumption from the total energy consumption by device, there are also accuracy issues with electrical meters. Another method of measuring electrical energy consumption is estimation based on the used technology. In my work, I employed a different method where I gather information about electrical energy consumption of individual operation performed by control plane, by algorithm implemented in the control plane. Of course, control plane as algorithm very often implemented in the software way. The control plane execute program, and this program is divided into atomic operation, such as arithmetic operation, addition, multiplication, division, and so on, functional calls, control statements such as conditional instruction, if, while, and so on, if, switch, and so on, and loops, for loops, while loops, and similar statement. To estimate the electrical energy consumption of the control plane, it was necessary to obtain information about the energy required by each atomic operation. In my work, I utilized results published in the literature regarding the electrical energy consumption of basis C or C++ language operation executed on AON and IRM processor. The table represented here, we have here 3 rows of 2 columns. Columns for operation and energy required by such operation. The table presented in this way show a comparison of individual operation with energy expressed, of course, in nanojoule. One operation consumes a very small piece of energy, so it's energy expressed in nanojoule. I used such information in my simulator that was developed in Omnet++ environment. The structure of this simulator is very simple. It consists of n traffic generators, one traffic generator per one input of switching nodes. Moreover, this simulator, the traffic generator generates a request for set up a new connection between inputs or outputs, or to transfer packets from input to output. Each operation of the control algorithm executed in the control module lead to retrieve data from the database presented here regarding the energy consumption of specific operation. The information was then from this database and from my request generator is sent to the statistic processor, where this energy is assumed to obtain total energy per operation. Numerical result. In my work, I analyzed 3 well-known control algorithms for cross-switching fabric. Control algorithms is mean path searching algorithms. It means the algorithms that are used to select which switching element in the middle stage will be used to set up a new connection or to transfer packet from input to output. The first algorithm is a sequential algorithm, where the search for a middle section switch through which a connection will be established start each time from the switch or switching element with the lowest index. For instance, each time we start from the top and we check if we can use particular switching element to set up or to transfer packet through the switching fabric. The next analyzed algorithms is the pseudo-random algorithms. The selection of the middle section switch or switching element checked for availability for the new connection is determined by pseudo-random number generator. And the last considered algorithm is the Benesch algorithm, very often used in telephone exchange. The order of checking the middle section switches is determined by the number of connections passing through each switch. The switch with the highest number of connections passing through it is selected as the first to check if we can set up using this switch a new request. If not, we will select the next switch, of course, in taking into account the number of connection of packets that are transferred by this switch. On the next slides, I present electrical energy consumption for switching fabrics with different capacities. It's been for n equal 32, 128, and 512. The charts show result of different control algorithm and different control traffic intensities. We can see energy consumption for sequential algorithm, Benesch algorithm, and quasi-random algorithm for different traffic intensity expressed in Erlangs. We can see that highest electrical energy consumption on all slides for n equal 32, 128, and 512 occurs in case of Banach algorithm. It is due to the necessity of arranging the switches checking according to a very load. Sequential and quasi-random algorithms exhibit similar values, although the sequential algorithm has slightly lower electrical energy consumption. Considering electrical energy consumption and the complexity of the control algorithm, we can say that sequential algorithm is perhaps the best choice for controlling switching fabric. It means the best choice for as an algorithm for path searching operations. And the final slide conclusions. In summary, the work presented a method for estimating electrical energy consumption in the control plane of closed switching fabric. The control algorithm required the last amount electrical energy was identified. Its mean sequential algorithm. It was also indicated that proposed mechanism does not increase the complexity. It was presented on the one of the first slide of switching node devices, as it utilizes mechanism already implemented in the device. Thank you for your attention.